All right, I'm back and we'll continue, okay? So in this lecture, I think we basically focus on algorithmic issues in connection with mathematical induction. All right. See, the very reason actually we study discrete mathematics is it's really foundation of computer science. We do need it, especially algorithms. Discrete mathematics lay foundation of algorithms. So here we'll discuss two examples to see how discrete math come into play. All right. The first question is, we want to compute nth Fibonacci number. How can we compute it? Of course, it's really trivial because we have recurrence already. We have recurrence relation. So it's very easy to write a recursive procedure or recursive function to compute the nth Fibonacci number. It's really trivial. For example, we can say that all right, so basically just return this one. It's very trivial. Of course, there are boundary condition. I will just ignore it. All right. So it's very trivial, and the correctness is obvious. We don't really need to prove it. So of course, the initial condition if n equals there's something. Okay. So I will ignore this part. But the key part is really this one. So we just use definition of Fibonacci number to write a recursive algorithm to compute it. It's trivial and the correctness is obvious. It's almost no need to prove that it works correctly. Unless you are not careful about initial condition, it's very trivial. All right. So anyone see a point to prove it works correctly? Of course, no need, I guess, for such a simple thing. All right. But actually, this one is no use in practice. Totally no use in practice. Theoretically, it can correctly compute the nth Fibonacci number, but in practice, totally no use because the running time of this one is very bad. It's approximately in the order of 1.618 to nth power. So it's growing exponentially. When n is large, you cannot get on. If you don't believe me, okay, you can try to implement this one in 5 minutes. I believe you can implement this algorithm in 5 minutes and try to compute F100 to see if we can get an answer before we finish the class today, okay? Or even F50. If you can give me this value before end of class, all right? So of course, this is not good. Another way is, of course, it's we can use another way to compute it by using an array. All right. Now, okay, that needs to be a little bit careful. Maybe start with 2 here. All right. So instead of doing it recursively, we can do it iteratively. So by using an array, boundary condition it's just needed to be careful. Okay. So we just again we use recurrence to compute fi based on fi minus 1 and f minus 2. All right. So it looks very similar to the previous one when we say return. So you compare with these two, it looks almost identical. But the huge difference is when we use recursive calls, when we want to compute this one, we do it again. We recursively compute this one. But in an array, when we want to compute this one, these two values are computed already. So these two values are computed already. That's a huge difference. So just as I write down the Fibonacci number, so that's how we do it. So when I want to compute 13, these two numbers are available already. So that makes the algorithm very fast. That's the algorithm very fast. It takes order of n time, roughly. Basically, it's order of n time. So theoretically, you are able to compute F100 using this one. But in practice, I doubt. In practice, 130, I don't think you can get it. You'll get overflow, I think, because number is too large. Your computer cannot handle it because the answer is too large. Okay, if only maybe 10 digits long, 16 digits long, or some, but I don't know if your computer can handle this number. Okay, because number of digits, maybe too many digits. 100, let's see, 100, maybe okay. 100 maybe okay, 20 digits or something, maybe okay. But anyway, if we large, 1,000, so it's fast, but number is too large. Okay. Now, so this was fast, but unfortunately, the space is used because we need a full array in order to compute n Fibonacci number. But in practice, when I compute it, I only need two numbers. So it's a kind of waste in terms of space. So it's not space efficient. So when n is large, I waste a lot of space. Space is precious. Okay. So now question is it possible to compute n Fibonacci number by using a constant number of variables or registers? I don't want you to use full array with n plus 1 numbers. I give you only a constant number of variables or register you can use. Maybe just a 4. Actually, essential part only two variables. Is it possible to compute n Fibonacci number? That seems possible, right? But basically, we only need to keep the last two numbers, the x and the y, in order to compute this one. Then we update it, right? So it seems we can do it in this way. All right. So if we just use two numbers or two variables to hold the last two Fibonacci numbers, that will be enough for us to compute the next one. Then we update it. Once we compute this one, we update this xy to these two. So this will be keep on moving from left to right. So using this idea, we'll be able to use only two variables together with two I and n to control the number of iterations. All right, so basically what happens is okay. Okay, so initially we start here. We start here. All right, so it's x, y. So this x, y keep on moving. So eventually we get this algorithm. So this one, inside what we are doing, just move this one position to the right. And for two variables, these two essential variables plus these two control, that's input, that's a control variable. So you can say 4 variables. But actually, these two are essential variables, just 2. Okay. You can say 4 variables or 2 registers. Actually, of course, in new implementation, there are 1, 2, 3, 4. Okay. But anyway, it's constant number of registers. So get this piece of algorithm to compute. So this one. All right. Now, for the previous two algorithms based on recurrence relation, it's almost obvious for its correctness, unless we are less careful, we're not careful about initial values. Otherwise, it's obvious. As they compute the nth Fibonacci number, there are no need to prove it. But for this one, it's not obvious at all why this one computes nth Fibonacci number. Because we don't really see any recurrence relation. Only thing we see that x plus y, here is y minus ix. So there's nothing to do with the Fibonacci number. So in order to claim that this one really computes nth Fibonacci number, you have to convince other people. So therefore, it means we need a proof that this one really computes nth Fibonacci number. But how can we prove it? All right. The most difficult part of algorithm is when it contains loops. The problem here is with loops, this for loop. Without loops, to prove the correctness, typically it's easier unless you are very, very uncareful. Otherwise, it's easy. I mean, easy, but actually not. So in fact, we make a lot of errors, typos, whatever. In my notes, I find some very, very stupid errors and typos. I have no idea why I put these things, okay, in my notes. But anyway, oh yeah, disclaimer again, remind you again. These notes is for my use, okay? It's just remind me what's going on. So there are some typos. Actually, I haven't decided whether I should change these typos or not. Actually, one way to leave these typos is if you can spot these typos, that means you understand these things. Okay, I haven't decided whether I should change these stupid typos. At least I found some stupid typos, even in the very beginning of the notes about induction. The basic step, I know something very stupid. For whatever reason, I have no idea. But anyway, so in this case, we do need a proof. So it makes sense. So that's the idea, we do it in this way. But does the algorithm really reflect our idea? It's really truthfully follow this idea to compute Fn? It doesn't need a proof in this case because it's not obvious at all. This one computes Fibonacci number. All right. So how can we prove it? Now, in this case, it's a very natural way to use induction of number of iterations. So because the main part of algorithm is just this iteration, it's a loop, goes n-1 times. All right, so it's very natural to use induction of number of iteration to show that certain thing holds. And this certain thing will enable us to show that indeed we compute nth Fibonacci number. All right, so let's see what we need. Okay, so in order to do that, we need some notation. Value of x, y changes. So it's better to denote value of x, y after each iteration with a subscript. All right, so eventually we get y, so that's yn. So in order to prove this one indeed computes nth Fibonacci number, what we need to prove is yn equals fn. Let's see, fn. Okay. So that's our statement. We need to prove this one. All right. Now, how can we prove this one? Because value of x, I, and y changes. Initially, of course, x0 equal initial value equal 0, y0 equal 1. That's their initial value. All right. before the first iteration. So that's their initial value. All right. Now, how can we prove this one? Yn equal f of n. For this one, of course, first we know this algorithm will terminate. After n minus 2 iteration, when I reach n, the algorithm terminates. Because it's for loop, it's a controlled number of iterations. All right. So eventually it terminates. When it terminates, we get the value yn, and we want to prove this one equal fn. So in order to do that, what we do is we prove something that always true at any time of the algorithm, so-called invariant. So our intention is y points to the current number in the Fibonacci sequence. So any time for this algorithm, we want to show that yi always equal fi. So one more iteration, yi plus yi become the next one, become fi. Sorry, yi plus 1 become fi plus 1. All right. So that's what we want to prove. So instead, in order to prove this one, what we do, we prove this one. All right. Now you see this. Now we get a statement about the integers, about natural numbers. So we have a base for, we can do it for induction with number of iteration. Induction on I to prove this one always holds. All right. So we'll try to prove this one. Okay. Now let's see. So if this one is true, then when I equal n, so this one will give us this. This is what we want to prove. But in order to prove that, we prove this statement. This is called a loop invariant, or just invariant. Invariant means something that does not change. Regardless of where we are in the algorithm, this one always holds. Okay. All right. So now we will use induction, and our induction hypothesis is before the ith iteration, the loop invariant holds. So that means whenever this k is less than I, then this one holds. All right. Now our purpose is to prove that yi also equal fi. So that's after ith iteration. So we exit loop one more time. We want to prove this one holds. Of course, then we need to see what's going on inside the algorithm. All right. So what we have is yi equals, by the algorithm, xi, sorry, I minus 1, okay, plus yi minus 1. So inside the algorithm, that's what we get. Now we know that this one by induction hypothesis, we know this one equals this by induction hypothesis. Induction hypothesis here. So we know this one equals this one. What we want is to show yi equal fi. But we start here. From here, we can see the value depends not only on this one, but also on xi minus 1. But induction hypothesis said nothing about xi minus 1. So here again comes with that idea. In order to prove this one, we need to prove something stronger. So in order to prove this one, actually we need something stronger. We need to add something. Also xi. We also need this one. Actually, that's our idea. So these first two values. Okay. So this one holds fi. This one holds fi minus 1. So actually, we need both of them. All right. So here we also have xk equals fk minus 1. All right. Now we can replace this one by induction hypothesis that becomes fi minus 2. So that's the recurrence relation for Fibonacci number. So therefore, that will give us fi. So indeed, now we'll be able to, we prove that this one. Indeed, after one more iteration, IC iteration, fi indeed equal fi. So induction step allow us to show this one equal this one. But that's not good enough, because in the statement we need to prove is also why xi equals this one. Not only we need to prove this one, we also need to prove this one in order for the next step. So we also need to prove this one. So after we've done that, we need to prove that xi, we also need to prove that xi equals fi minus 1. So we need to prove something more. So in this case, what we get here is xi equals y, this new y. Okay, so this yi. This x is old x, xi minus 1. Now using induction hypothesis equal here yi equal fi. This old x, so it's fi minus 2. So that gives us fi minus 1. So indeed, this one also holds. All right. Now by induction, we know everything here holds. And then when our algorithm finishes, indeed, this y is yn. So yn equal fn. So indeed, the algorithm will give us answer f of n when it finishes. So induction step tells us this. All right. Is it clear? Any questions? I take a look. Yeah, once you just send me 100th Fibonacci number from Google, I think that's too large for your computer. Okay, with how many digits? About 20 digits. For computer, maybe too large for your notebook. So even with array may not work. Okay. All right. Now, everyone convinced, or you have a question? Actually, some students notice something. Okay, that's very good. I intentionally made some mistake, small mistake in the algorithm. Something we were missing is the basis step. So here is the induction step. So you see, the induction step has nothing to do with the initial step, initial values. So suppose our initial value say give x 5, this one 7, this whole thing still works. It still proves these two things. Therefore, we have to go back to basic step to see if it holds for the basic case. It turns out it does not work for the basic case. Okay. So basic step. For people that remember, we know there are two, first one and second one. So these two. All right. If you look at this one, for n equal 1, so we do not execute this one. It does give us value 1. N equal 1, it does give us value 1. But for n equal 0, it also gives us value 1. So it's incorrect. After that, it gives us correct value. Does it give us correct value? Okay. For 2, it gives us 1. For 3, it gives us 2. After that, it works correctly. But for n equals 0, it does not give us correct value. Because y points to the second one. So, but we'll print out the first one. We need to print out the first one when n equals 0. So this one does not quite work. Easiest way to change it, in fact, is the following. To make it work, okay. Now, the idea here actually is to add a number here. That's f minus 1. So instead of this one, we have x, y pointing to these two. So here position minus 1, here 0. So then y give us correct value for when n equals 0. Y0 equals 0. All right. Then it executes n iterations. So this part is guaranteed by induction already. We only need to see whether the initial ones are correct when n equals 0 and 1. All right. So it just starts with 1 0 instead of 0 1. It's just a coincidence. It's just 1. It's just coincidence. It's 1. So these two values add up to 1. So therefore, this one is 1. Just extend the definition of Fibonacci number to minus 1. Then the whole thing will work. All right. Okay. So here two important things. One is loop invariant. In order to prove an algorithm works correctly, when it involves loops, the most important thing is to find the loop invariant. It's not easy at all. This one is the recurrence relation. So again, we see recurrence relation come into play. So here is loop invariant. So that's the most difficult part. Find the loop invariant. Find the recurrence. Once we have that, we use mathematical induction to prove it works. In the meantime, don't forget the importance of basis step. Originally, when we set 0, 1 here, it does not work because of basis step. It does not affect the induction step. However, it does not work because of basis step. So be careful with both basis step and the induction step. Okay, I have to emphasize it again and again. Both basis step and the induction step, both are important. So typically, basis step is trivial, but it's very important. Difficult part is induction step. And the essential part, the most difficult part actually is to find invariant or recurrence relation for induction. Okay. All right. Time runs very fast. I thought only 15 minutes about for this one. But anyway, it does not matter. Okay. Okay, so here is a small algorithm that do something with two natural number x, y, and eventually will output p as a result. So it's a very simple algorithm, right? There's a loop here. So keep on going whenever y is positive. Keep on going until y equals 0, it stops. So algorithm will finish because each time y will be halved. This is a floor function. For any number, maybe use alpha maybe. This is called the floor function. At least the largest integer solid. At most alpha. So for example, 3.15, it takes the floor, so it's equal 3. If it's a negative, so then it's 1 less, it's -4. If integer, then it's itself. Okay, so that's floor function. If x, y binary, then this one is we shift one position to the right. This one shifts one position to the left. If it's in binary, all right. If twice of this one, so just shift this one position to right. It becomes add a 0 here. So this one divided by 2. Take floor, we just shift one position to the right. So that's very, very simple operations. In decimal, it looks like this. In binary, actually, one is left shift, one is right shift. All right. So each time we'll do a double x and half y. So we always do that. With one difference is when if y is odd number, x will be added to p. So what's the function of this algorithm? So let's try one small value to see what it does. So initially p equals 0, say x equals 3, y equals 6. All right. So we check. So this one will be halved. This one will be doubled. Oh, sorry, halved. Okay. Half of 6 equals 2 plus 1. Okay. All right. So p does not change. We'll do it again. So this one will be halved. This one will be this one will be doubled. Y will be halved. Now this one is odd. So 6 will be added to p. So p becomes 6. All right. Now this one will be halved, become 0. This one will be doubled, become 24. Now because this one is odd, 12 is added to p, it becomes 18. Now y becomes 0, so the element stops, and we output 18 as a result. So that's how this element does. All right. So what's the relation between p and xy? In this particular case, it seems that p equal product of xy. But is this really the case? It can be just 2 times x plus y. It's also equal 18. Right? Or maybe something else. How do we know? Is this one or this one or something else? It's not quite clear at all from the algorithm. So we really need to prove if we think it's computes product of x, y. Do we need a proof? Do we deserve a proof? Really, it calls for a proof. Because it's not obvious at all. It doesn't need to see. It seems to be the case, but it's not obvious that indeed compute this one. All right. So we need to prove it. All right. So indeed, we'll prove it's a compute product of x, y. So I want to make the statement. Indeed, the algorithm indeed compute product of x, y. All right, we need to prove it works correctly. So how can we prove it? The problem again is it involves loops. So we need to prove is regardless of how this loop goes, it always gives us correct answer. All right. As before, we need some notation. All right. Okay. So let's x, y, y, I, p, I respectively represent the value of these three variables after ith iteration. So algorithm will terminate we know the algorithm will eventually terminate because each time value y is reduced by half. All right. So this one is roughly in the order of log 2 of y. So it's roughly this many times. Number of iterations is roughly this much. But actual number does not matter unless we're interested in the running time. Otherwise, we know it will terminate. All right. So algorithm always terminates after so many terminations. And after terminates, we want to know, to show that p star, pi star equal x1. That's what we want to show. In order to prove the algorithm correctly, compute xy. Okay, maybe to emphasize, correct? All right. Now, how can we prove it when it terminates? So again, here very naturally induction come into play because number of iterations. It involves number of iterations. So we use induction. On the number of iterations. So what do we need to prove based on number of iterations? We cannot say that we prove this one based on I, because we don't see I here. So we need to find something related to I. So we need to find the loop invariant. So what is loop invariant? Something that always holds. It's not trivial. Actually, in this case, it may not be easy to find it, to spot the loop invariant. All right. So that's the recurrence. That's the recurrence. So after iteration, we always have this result. Product of xy equal product of xi, yi plus pr. So what does that one tell us when algorithm terminates? When algorithm terminates, so this looping balance must be useful for our purpose, otherwise totally useless. So in this case, that one is useful for our purpose because when it terminates, when algorithm terminates, what happens? We have yi star equals 0. This by it terminates. It cannot execute one more loop. All right. So if we plug in that looping balance, what we get? We get xy equal xi star times 0 plus pi star. That is exactly pi star. So when the algorithm terminates from the loop invariance, we get this one. So therefore, when loop terminates, this value of p exactly equals x times y. So that's what we're going to prove. All right. Let's see time. About running out of time. Okay. Now for this one, the initial step, the basis. Again, we need to do two things. So maybe easier to do the basis first. I equals 0. So what we have x0 equal x, y0 equal y, and p0 equals 0. Indeed, it holds. This one is 0. So initially, we do have xy equals x0, y0 plus p0. So basis step holds. All right. So we only need to work with induction step to show this one always holds. Okay. Since time's up, actually, I strongly encourage you to try it yourself. I will quickly go over it on Wednesday to see if you can come up with the induction step by yourself. So we prove this one use induction. There are two cases. You need to consider. It's easier to consider two cases based on y even odd. You have to look into algorithm to see what happens eventually to get this one after one more iteration. So I really strongly encourage you to try this one by yourself before Wednesday. If you know how to do it, that means you know induction, you know how to use induction. Otherwise, you need to spend more time on induction. All right? Okay, I think I'll stop here. And I strongly encourage you to try this one before Wednesday. I'll continue on Wednesday. All right. A reminder that homework is due tonight by 5 p.m., I think. Late submission is only acceptable one day up to 5 p.m. tomorrow with 20% deduction. All right. And in case you have trouble to submit your assignment online, send an email to one of the tutors, Su Chong. Okay, and maybe I remind you again. Actually, when you submit, if you have problem, it will remind you to send email to Su Chong for submission. All right. Okay, so that's it for today. See you.